Good morning and welcome back. We are very happy to move on to the last chapter of electrodynamics. Chapter 14, radiation by moving charges. It will be divided into two types of motion. One is constant motion. I will show you a linear Chart potential which can solve a constant motion. Second, I will show you the acceleration or deceleration. Okay, that will be related to synchrotron radiation. So synchrotron radiation is very important in this chapter. One of the most important applications of radiation by moving charges. Today, we will cover ED. And what is the day? 27. Okay, page 1 to 15. We will cover 15 pages, but 4 pages are optional. So if you have time, you can study those 4 pages by yourself. The details. Okay, first, let me show you. We will review the basic equation, the wave equation. For example, Laplacian V here. Laplacian A, that's the wave equation with the source term. That's inhomogeneous source term. Inhomogeneous source term. So in general, we can write the wave equation in this form. Remember here, 4 pi. 4 pi is because of Gaussian unit system. And 4 pi over C is, once again, Gaussian unit. SI unit is here. That's SI unit. Okay, so here we have a general form of wave equation that has been discussed in here. Okay, so we need another one, that is the green function. The green function should satisfy these relations. This one. Okay. Let's retard the green function. With the outgoing, the solution of this green function is shown here. Okay, sorry, it's not clear. I should be careful. This is the green function. And this is the retarded green function, the solution. Just like the old one, but except we have a delta function here. And these two have a simple relation. Green function, incoming wave, together with outgoing wave boundary conditions. So wave will come from inside out. Okay, that's the green function. So we will use this green function. It's a general solution. This general solution allows us to find the solution of phi and A easily. The expression for phi and A will be very simple. Okay, now let me apply 6.45 by assuming that the incoming wave is 0. So scalar potential and vector potential, they have the same form, similar form. Okay, from this green function. This is source term, okay? With this source term, we can calculate phi and A. Now we need both phi and A to specify E and B, unless the source has harmonic time dependence, just like in chapters 9 and 10. Here is a qualitative qualitative picture of radiation by an accelerated charge. The charge is at rest first. It's at rest. Okay. So initially, E field line surrounding a stationary charge, stationary 没有移动的固定的 fixed in a space, and then the charge is accelerated suddenly. A fraction of E field, this part of E field lines, showing the effect of charge acceleration. Charge acceleration. Okay, that means the charge particle is accelerated. So what happened here? So the field line here and field line here, there will be a discontinuity. It's still continuous, but due to the acceleration of the charge particle, the field line will distort. Yeah, so just like when accelerate, and the field line will propagate at the speed of light c. Therefore, it will distort here in this region. Just like we generate a radiation from the charged particle. Okay, that's the basic picture. And now we use a linearity chart potential and field for a point charge. What is the linearity chart potential? It's shown here. Linearity chart potential is related to this green function. And especially for a point charge. For a point charge, rho and J due to a point charge E. E can be positive, can be negative. So E carries a sign moving along the orbit. So the charge moves along the orbit here. Moves smoothly. That's the orbit. That's the orbit of the moving charge. At the velocity, that's instantaneous velocity, instantaneous tangential. So it's instantaneous velocity. Velocity V, we should change our pencil. Velocity is just equals the R, the T prime. What is the difference between prime and unprime here? Unprime is the observer, and prime is the source. Is source, not two coordinates, unlike our definition in chapter 11. Chapter 11, prime and unprime represent two inertial frame, two Lorentz frame. But here, prime and unprime just indicate our old understanding, source and observer. Source and observer. Source and observer. Okay, so delta function is easy. just here. So which just indicate at time t prime, the delta function should be exactly at here, the orbit, 轨道. It can be a circular motion or constant motion. Can be any type of motion. But for our convenience, we just draw something just like a circular motion. And J is related to rho times V. Rho times V. Okay, so J is the volume current density. By substituting this one and this one into here, we have a very simple relations. We can evaluate this point charge. Remember, point charge. Just one charge. One charge can be positive, can be negative, doesn't matter. So the solution here is called R. That's the definition. That's the separation, the absolute value of the separation between observer and source. Separation between source and observer. And beta. Beta is the velocity, normalized the velocity with respect to the speed of light. So it's a normalized velocity, always less than equals to 1. Okay, so that's beta. The value of beta. Beta is the same, similar, but evaluate at source time. Evaluate here. Evaluate at source time. Okay, here is the difference. It becomes observer and source position. Okay, so we have a very simple phi and A for potential. 3 component S, A, Y, A, Z. And here is just 1 component. So 1 plus 3. Totally, we have 4 components. But here, we just write in this form. It looks very beautiful. So we give it a name. Oh, no, not yet. We still need to perform the integration. But the integration you can expect should be easy. Okay? Let me rewrite this equation again. This equation tells us that up to this point, easy. And let's rewrite this equation into, we define T prime plus R, T prime plus here as a function f of T prime. The definition of f of T prime is here. That's the definition. So we just rewrite this equation into this form. So interestingly, the T prime, so T prime, T prime, T prime, T prime, T prime. Okay, so we will use the delta function identity, this formula, which we have learned in chapter 1. Remember, if you don't remember, that's okay. Just open your lecture note to chapter 1. Chapter 1. If you don't remember, if you remember, fine, just use this idea. So that's the delta function, f of x. We will evaluate f of x exactly equals a. So xi is the solution of f of xi equals a. Okay, so we will sum maybe more than 1, but in this case, just 1. I will show you if we have times. we have just one time only, just one time, and no more. So just 1 point, no other contribution. Okay, we will use this property. So eventually, the derivative and phi here, phi is 1 over r t prime, and evaluate at retarded time. That is the time when this one equals t. That is t prime plus, sorry, change our pencil. T prime plus separation t prime divided by c equals t. T is the observer's time. That's the source time. Source, and then it takes time to propagate. Go back. It takes time to propagate. So take time to propagate from the source to observer. Therefore, they have a simple relation. This time is called retarded time. Retarded time. Actually easy. So no matter the source is moved to observer or leave observer, it always travels at the speed of light. That's the universal speed of light. C is always the same, universal speed of light. Okay, Si is the solution of f of xi equals a. Okay, one more time. That's retarded time. Retarded looks like 延迟的时间，可是事实上是比较早发生的时间。source 发生一个事情发生之后，这个事情发生在 t prime， 它需要传到 observer， 需要比较晚的时间，这个是 r， 它需要的时间就变成 r over c， 就好像这是一个 sun， 那这个是一个 earth， take about 7 minutes and 30 seconds， 7分30秒。Okay, so if we want to evaluate the temperature, if we want to evaluate the the sound we see at this moment is actually 7 minutes and 30 seconds before. So it's the idea of the retarded time. Okay, so by substituting this idea, we got this one. We got this one. This is the retarded time. And E beta here, R here, and this one here. Evaluate at the retarded time. Evaluate. 我们就是在它 retarded time 发生的时候去看它的。OK， 这个 idea 我们已经讲过很多次了，所以大家应该比较有感觉了哈。那这个值是什么呢？ Let's have a look at this value. Actually, this value is not that difficult. Cross. Hey, Siri, sleep. No, I don't need you. Sleep. Yeah. As you can see here, I use an iPad. Sorry. I use notebook plus iPad. Because Apple Pencil very good to write, very convenient. That's why we use notebook plus iPad. We also use a different combination, notebook plus 手写版 Wacom, for example, and not good for handwriting because we find the relation between 手写版 and the screen. To find their relation is not that easy for me. So personally, I prefer notebook plus iPad, much more easier to understand. And here, so the R dt prime can be write into this form. R is the absolute value of observer and source. So in terms of this one, observer, source, okay? X is a fixed position, independent of time. Okay, let's just assume the observer is at point here, a fixed position. So this one differentiate with T prime. So no contribution here and no contribution here. This one will give us beta. And this one will give us 2R dot dr dt prime comes from here, comes to here, okay? And 1/2 give us 2 move to here. And 1/2 becomes 2 from the numerator to denominator. This part the same, okay? And this one is R, the same. And this one, that is the speed of light, right? Sorry, the speed of the particle, V, sorry, V T prime. That's the speed of the particle here. And here is -2. We have 2 here, 2 here, 2 here, cancel. And just move the minus sign to the front. So we have an X minus R T prime. And this is the R. So just these two from here to here, from here to here is just normalized with R. That's the direction, unit vector. That's the unit vector. So N is unit vector T prime. Here is just like X minus X prime. Sorry. Unit vector X minus X prime. But this time we express X prime as R T prime. Okay, slightly different expression. Okay, so N just from observer to from source to observer, from source to observer. Once again, from source propagate to observer. Therefore, it becomes VT prime dot NT prime. So this one is, once again, this one is very easy, just one, very easy. But this one gives us R here divided by C. So it's beta. Normalize the velocity dot the direction from the observer, from a source to observer. Okay, which is defined as kappa. Kappa. This is less than 1. This one is the direction, so it's univector. Therefore, this one is less than 1. Therefore, kappa should be greater than 0. Greater or equals to 0. But you know, particle cannot exceed the speed of light. Particle always beta. For any particle, always less than 1, always. For wave, they can exceed the speed of light, but for particle, no. Always less than 1, always. Much better. I improve my teaching skill. Use Notepad, I can improve my teaching skill a lot. Therefore, here, you don't have to define kappa, actually. Just have an idea. Substituting equation 5 to equation 3. Where is 3? 3. 3 is here. This is equation 3. Okay. We eventually have a simple expression that has a very famous name, Linearity potentials. Linearity potential. Okay, very famous. Why it's famous? Because easy. Because very easy. Just imagine if beta, the particle is at rest, stationary, do not move at all. If particle do not move, therefore, will be 0. Beta exactly equals 0. So phi just simple R over E. A very simple. Stationary. At rest. Yes, so very easy and very convenient, very easy to understand. Linear, L-I-E-N-A-R-D, linearity potentials. Okay, fields for a point source, for a point charge, we have a linearity potential. And this is the integration form, to be integrate. And that's the optimum. That's the after integration. Which one is more convenient? No, cancel. 不需要. Hey Siri, turn off. Just a moment. Okay. I don't know. To obtain E and B, we need to differentiate 微分，对 phi 跟 A 都要做微分 with respect to X and T. Yeah. And the right-hand side of equation 14.8 depends on X. okay, depends on x through n and r。这里面有没有 x 的 dependence？ 有啊。Remember, r is x minus r t prime. Therefore, r has, okay, second, n. What is n? N is r over r, right? That's definition. Therefore, it also depends on x with respect to x. But right-hand side of equation 1 here depends on x through r only. Yeah, just one component, r. Beta independent, t prime independent. So hence it's more convenient to use equation 1. We might expect equation 14.8 is very convenient, but actually it's not. It's easy to understand, yes, we agree, but very difficult to operate. Integration form is more convenient. This is the integration form. It's more convenient. Okay, it's more convenient to use equation 1 rather than equation 2. Okay, so we have potential in terms of integration form. Obviously, the next step is to calculate the E field, the corresponding E field and B field. Let me show you how to calculate the E field. We have a scalar potential, vector potential. We can let f of r to be any function of r. And we want to differentiate with respect to this position. R is x minus r t prime, absolute value. So if you want to differentiate this one, gradient of this one, this is a scalar. What will happen? We use a chain rule with respect to r first and then perform this gradient. So we differentiate, we find the total derivative f dr, then we perform this one. And this one is easy, just give us this one. We already studied this one before. You don't remember? Yes, here. We already studied this one. Very similar with respect to x. So this part is easy. This part is very easy. Okay. This part just give us n only. Okay. Very easy, just write it down and you can see here, give us n t prime. It's a unit vectors from the observer source to the observer, unit vector. So this one will give us a simple relation. EXT, we need electric field equals minus gradient phi minus 1 over c partial A partial t. Okay, and we can use these properties in chapter 1. Okay, so gradient phi is shown here. Two parts. First part, gradient phi, consists of this one. So this part, denominator, give us this one with a minus sign. And with respect to r, give us this one. Second, here, with respect to r, give us this one and this one. So this one is actually very easy. Yeah. Let me change. Easy. Easy to understand. Simple. But remember, we have an integration sign here. We need to perform the integration. Second, this one. Partial time derivative of the vector potential and with respect to t. So only here, with respect to t, it gives us a minus sign. Okay, others are the same. Similar idea. We differentiate with this one first, and then just assume this one as a function. Or you can rewrite this one, rewrite this integration, and eventually just give you a simple relations. E comes from here, E, and minus sign here. C comes from here. Others are the same, except here. Oh no, the same. And this part is still the same, right? So the integration is easy. This one is easy, but not finished yet. We still need to perform the integration. So looks easy. What else? That's electric field. And for the next 4 pages, they are optional. You can study by yourself. Or if you don't fully understand what's going on, you can check the next 4 pages. Okay? You can check by yourself. 2, 3, 4. Yes. Or here. 11. And we will resume from here. So eventually, we have 2 expressions. One is E field. We have 2 expressions. Let's skip the mathematical detail and focus on its effect. This one eventually gives us E field. Maybe we should go to page 7. Up to this point, looks easy. But if you perform the integration, it will be, perform the integration, it can be divided into 2 parts. Okay, if you do not understand, you can check page 8 to 11. But if you have some idea, yeah, focus on the physics itself. That's the most important part of this chapter. Okay, so we will have this one. The first term is related to velocity field. It depends on 1 over r squared, just like our previous understanding. And the second part is interesting because it depends on beta dot. That's acceleration. That's acceleration. Normalize the acceleration. Normalize. Okay? So velocity field is the field we already evaluate at retarded time. So an acceleration field will be a new to us. We will consider beta dot, this part. Let me draw this one. That's the most important part. Why? Because it depends on 1/r. Therefore, at far field, this one will become very large, much larger than this one. Much larger than this one. Acceleration field is more important than velocity field. Sleep. Series sleep. It doesn't matter. How about the magnetic field? Magnetic field, since this is related to far field, so they have a simple relation, just like the wave outside the source. We already studied this one before in chapter 10. Chapter 10. Okay. Outside the source, E field and B field has simple relations outside the source. Okay, so we divide it into two parts. Let's discuss let's have some discussion. First, the velocity fields are essentially static field, falling off as exponential, 1/r square. Static field 跟我们静电静磁讲的都一样 1/r square. However, for the acceleration field, equation 13 and 14 shows that E and B are mutually orthogonal, 正交, as a typical of radiation field. 这两个在 radiation 的时候，从这里发射出去，在这边看到的 E 跟 B 是 perpendicular， 然后 E 跟 B also perpendicular to N. OK, mutually orthogonal, 彼此是正交的。Like E cross B pointing vector, point wave propagating in the direction of X. X is the direction of N. Okay, so they have a simple relations. Unit vector N points from the retarded position. R T prime. This is the retarded position to X. Okay, 就是从这里 from here to here, from the retarded position to here. One more time, to here. But it's unit vector. And T prime are quantity in the same reference frame. Same reference frame. 一样的 inertial frame, 就是同一个坐标系统里面 same reference frame. OK, 所以很方便哈，跟11章讲的不太一样，不是同一个情况。 Okay. Velocity field again, acceleration field again. E and B are in general has a broad frequency spectrum. 宽频的哦，不是窄频的哦。因为这个地方 since we have derived these two equations, these two from equation 9.2, which applies to a non-dispersive medium. In this case, the so-called non-dispersive medium is vacuum. 真空 no material inside. Signals at all frequencies travel. 这边既然没有 dispersion， 就是所有的 particle 速度都一样，没有射散。没有射散 phase velocity that's group velocity， 然后这是一个 constant phase velocity 也是一个 constant， 在这边 C， 在这个两个 case vacuum OK， 这是因为这两个 special case and E and B at T depends on instantaneous motion of the charged particle at a single retarded position。对，它们 depend 只有在某一瞬间的速度。At T depends only on instantaneous motion of the particle point charge at a single retarded potential. Once again， 就是我们虽然前面的时候有讲到，它是一个可能会有很多个，可事实上在这边只有一个点，只有在这个轨道上的某一个点才会有贡献，其他都没有。One and only one。你不可能大于光速，它的条件就在于这个地方。The speed of light, you cannot exceed the speed of light. Therefore, just one point. One and only one. One and only one. Okay. Go back to page. Go back to here. Remember, we can sum over more than one root, but here we just show you. Actually, we have only one, no more, just one, because we cannot exceed the speed of light. The maximum speed will be c. So that's a pretty good argument. Okay, last page. Quantities in the brackets are to be evaluated at the retarded time. Evaluate at the retarded time. Source happen time, which is here. So where the orbit is a specified function of t prime, plus t prime depends on x and t. This makes the final expression for E a function of x and t, as shown on the left-hand side of equation 14 here. For the same reason, the unit vector n t prime in equation 14.13, hence the final expression for B also depends on x and t. OK， 这是一个论述哈 ，evaluate 在这里。好，这边讲完了，只剩最后一页 ，last page。The relation between observer's time t and the retarded time t prime is here。很简单，事情发生的地方 retarded time 它需要时间传递。Indicates that a signal from the charge travel at the speed c toward the observer, independent of the motion of the charge. That's the universal speed of light. UNIVERSAL, speed of light. Universal speed of light, the same speed. Here is now let me show you an illustration, 一个图示 of the time retardation and length contraction. Computer generated graphics shows the visual appearance of the three-dimensional lattice of rods and balls moving toward you at various speed. 就是有一个结构，有球，有棒子，球，棒子，棒子，棒子，球 moving toward you， 这个系统向你靠近。Normal view， 如果速度不够快的话，你看起来会就是这样子。速度快一点 0.5 倍的 c， 看起来还是很像。At 0.95 speed of light, the rod appear bent, and the ball, the rod is bent, and the ball is also distorted due to length contraction. Perpendicular do not change, but this direction will contract. So they will change their form. So when the particle move at very high speed, like this one, lattice appears severely distorted. 变形了。它不再是你看到那个世界 ，distort, severely, 严重的，非常严重的，它很严重的变形，所以看起来好像东西会集中在你的前面。本来这边 at low speed we have a large hole, but at high speed the hole becomes smaller and smaller and smaller. Okay, so I remember when I was an undergraduate student, I saw this animation, this illustration. I was very surprised because I do not expect to see this kind of effect. Surprise. Now, because of the computer, we can simulate the view we will see at extremely high speed. Okay, so let's visualize 视觉上的效果，我们就可以模拟出来。所以这个模拟会比较 realistic 一点，而不是纯粹想象的。很实际哈，世界会因为速度变形，所以一个 electron， 如果我们有一个 electron， if we have an electron move at very high speed, then the electron will see the world in a different shape. Yeah, very interesting. This is the end of today's course. Bye-bye and see you next time. Stop.